All right. The vast majority of you, of course, got hundreds on the review questions, which some rather interesting wording that got carried by a group of people. So again, there's nothing that says you can't work together on those. But because everybody did so well, I actually thought about giving you a quiz today that was just your review questions. Since so many people got 100 on the review questions, then you know it so well, then we should be able to quiz on it well too, right? That's just one of those things that hopefully if you work together with people and you decide upon a correct answer that you actually, you commit to it, you learn, you actually know the answers, you're not just getting the right answers down on the turn in to get 100 in the book. But it does help. So let's go ahead and spend some time going over the review questions, and then by request we'll go and look at number 10, from the practice problems. I apologize. I am fighting a cold / think it's becoming flu. So I will be here for you as much as I can. I haven't taken a sick day since I've been in Louisville, so I'm trying to keep that record going. But I keep getting these chills and my forehead keeps getting damp. It's like nasty. By request, some people asked if they could take the exam on Thursday rather than Friday. I'm willing to do that. As a matter of fact, if you think you're not going to be able to take it on Friday, since I have to have my grades turned in to the school by noon on Friday, we're kind of cutting it close with the last date. So if you feel you're prepared and can take the exam on Thursday, we'll go ahead and do that. For those of you that don't take the exam on Thursday, we have yet one more opportunity to review before Friday. For some of you, though, you really do need a good score in the books. So if you know you're not going to be here Friday, don't say, well, I missed it, I can just take it Monday, because I can't go back and change the grade for the grading period once we roll to Monday. It really is you need to take it, okay? Study guide questions for Module 8. Define stoichiometry, also known as stoichiometry, but stoichiometry, and explain why it is such a useful tool for chemists. I'm going to go ahead and have the book answers in front of me too, so make sure that I read them in case there's some nuance to the answer they want to make sure we get. But let's just speak generally about stoichiometry. What's the basic principle of stoichiometry? What are we doing when we do a stoichiometric problem? Okay. Comparing, relating, right? We have a balanced equation, and we're relating quantities of one material, one molecule or one atom in the reaction formula to not only another one, but something that's different with chemistry is you can relate it to every other one. Now, the few of you that didn't get hundreds, it was because I got really nitpicky on some wording. Like if you came back and said comparing masses, sorry, you lost at least 3 points just for bringing up the word mass when talking about stoichiometry, without saying converting to moles, because you can't relate masses to masses. We're relating moles to moles, okay? So you should expect a question like that. Can you compare masses to masses using stoichiometry? Now, we know we can take a mass, convert it into a number of moles, and then relate it using stoichiometry, but you can't relate it directly, mass to mass, using stoichiometry. You relate it indirectly using stoichiometry. Okay, so you got the difference there? We can also use volumes for gases using the Gay-Lussac law, right? We can compare those stoichiometric coefficients, also relate the volume of gases, but only the gases. So the stoichiometric coefficients help us relate any product or reactant to every other product and reactant, not just any other product and reactant. It relates to all of them. That's one of the real powerful things about stoichiometry, is you know one, you can figure out how much you would need of every other reactant. Let's say, if we're talking about a reactant, if you know one of them, you can figure out how much you would need of every other one of them, and you would know exactly how much of every product you would produce simply by knowing the quantity of one of them. Okay? That's before we get into the idea of limiting reactant as well, which we'll cover in just a few moments. So the book says that stoichiometry is the method used to relate the quantities of substances in chemical equations. It's useful because the quantity of just one substance in the equation, from that we can learn something about the quantities of all other substances in that equation. So some of you limited your answers to, if I know a reactant, I can figure a product. That's true, but that's only part of the answer. If I know one of them, I can relate it to any other reactant or product. Okay? Number 2, explain what a limiting reactant is and why is it important in stoichiometry. Real basic answer. What is a limiting reactant? It's the reactant that what? Runs out. Right. It's gonna be completely gone. And when it runs out, what does it do? Right. The phrase I used before was it stops the reaction engine. Right. Think of it as an engine. This is a process that's going to take place, and it's going to keep happening until it runs out of raw materials to make the finished goods. Think of an assembly line. You're putting together some component. Well, you can keep making components as long as you can keep making products. Ford's a big deal around here, right? Apparently. Okay, so I'm not from local, so sorry about that. Last night I noticed as I was watching one of my television shows that there were 2 cars that were, if you watched it, don't yell at what it is, but they were playing chicken. They were running at each other. And one of them was a Chevy, had a nice big emblem on the front. The other one was a Ford. You see the little circle on it, and they had covered it over with tape so you couldn't read it. So they were doing brand marketing, in the middle of the show. But anyway, for Ford, let's say you're putting together a door. And so you got different components. You've got the body, outer body, the inner door, you've got the glass, you've got the crank, you've got all these parts, right? You can keep making doors as long as you have all the parts. But if you run out of one of the parts, you got to shut down the assembly line. Because you can't say, you know what, that door handle or that lock button, that's not such a big deal. A bunch of whiners. I'm going to just keep making doors, but I'm going to leave out the lock button. It's not going to happen, right? They're going to stop the assembly line. So in chemistry, the same kind of a thing. As long as I have all the raw materials that I need to make the finished good, the reaction engine will keep making product. But as soon as one of them runs out, it stops. And the one that runs out is the limiting reactant. Now it's significant because of what? If we know the limiting reactant, what can we then figure out? Right. If we know the limiting reactant, we can not only compute how much product we will make, but we also know how much of every other reactant will be used. Okay? So, once we run out of something and the engine stops, we will have consumed a certain amount of every other reactant. And if we're given that we have more, we know how much excess of every other reactant we have. But if we go back to our parts bin, whatever was the limiting reactant, it's going to be all gone. And in product, we're going to have a certain amount of product, but once the limiting reactant is hit, no more product is made. It stops. Because it needs every component to keep making according to the reaction engine, according to the stoichiometric equation. So the answer from the book is that a limiting reactant is the reactant in a chemical equation that runs out first. And it is important because its quantity determines the amount of products produced. You can't make any more if you run out of a component. So it stops the reaction engine. Third one. A chemist experiments with the following reaction. We got 14 hydrochloric acid and potassium dichromate. Goes to 2 potassium chloride, 2 chromium chloride, and holy mackerel, there's a lot more stuff in there, isn't there? 3 plus 3 Cl2 plus 7 waters. Okay. I think I've got that right. Somebody just want to check me real quick. 14 HCl plus potassium dichromate, 2 potassium chlorides, 2 chromium chloride, 3 chlorine, and 7 water. Okay. Sorry about the wraparound. It's a little longer than I expected. So a chemist does the following experiment, or does the following reaction. If he adds 15 moles of hydrochloric, so 15 actual, to 1 mole of potassium dichromate, what's the limiting reactant? What are we going to run out of first? Right. You should see we're going to run out of, in here, the potassium dichromate, right? We're going to run out of this first. How do we know? Well, in a balanced reaction, according to this equation, for every 1 mole or molecule we use of this potassium dichromate, we consume an additional 14 of the hydrochloric acid. So the reaction equation is 1 to 14. We're actually given 1 to 15. We're given more of this one. See that? If it was, 2 to 29, it'd still be the same thing. It's just that we were given proportionally more hydrochloric acid here than were required in the equation. Yeah, Gino. We were told we were given 15. The question says, if he adds 15 moles of hydrochloric acid to 1 mole of potassium dichromate, which one's the limiting reactant? So this is, yeah, correct. This is the balanced. So for every 1, I need 14. Well, I have 1, and I've been given 15, which means I have, what's the phrase we use for this reactant now? We have it in excess, right? We have excess. It just means we have more. That's why in an equation, if they said a chemist adds 1 mole of potassium dichromate to excess hydrochloric acid, what they're doing there is telling you what the limiting reactant is. They're saying it's going to be potassium dichromate because you've been given excess. You've been given more than you need of the other one. Okay, so that's the chemist's way of saying my limiting reactant would be potassium dichromate if I've given you 1 mole in excess hydrochloric acid. In this case, given 1 to 15, you should be able to look back at your balanced equation and say, hey, it's 1 to 14, I've been given 1 to 15, this one is in excess, therefore this one is my limiting. And whatever product is going to be made is going to be based upon the relationship between this one and its stoichiometric coefficient in the balanced equation for everything else. Okay, so at the end, in the end, let's say we actually reacted this much together, we would have 2 potassium chloride and 2 chromium chloride and 2 chlorine gas and 7 water, and what would still be left over? 1 mole of hydrochloric acid. Because 14 of them would be used up by this potassium dichromate, and 1 would still be left waiting for more potassium dichromate to show up to run the reaction engine some more. So if we added 1 and 1/14th, never mind, I won't get into it. That's just me having fun. Forget that thought. Just don't even go there. Yes? You may. You're going to miss something critical for the exam, but that's okay. You've got enough other, you understand it so well, it won't be a problem. I'm kidding. Go ahead. Let me check in the book real quick after making that emphatic statement. Yes, the limiting reactant is potassium dichromate because 14 moles of hydrochloric reacts with 1 mole of potassium dichromate. Since 15 moles are added, 1 mole of potassium chromate will run out, and there will be 1 extra mole of hydrochloric acid. So far, I'm going to get 100 so far. Here we go. Number 4, state Gay-Lussac's law and explain how it's used. So again, Gay-Lussac, just basic definition. What is Gay-Lussac's law?
You can relate the volumes. Is that what the law is, or is that what it says?
That's the law. Yeah, go ahead and, what is it? So you're relating the volumes of gases in a balanced reaction equation. You're relating the volumes according to what? According to their stoichiometric coefficients. Okay. So in that, the last one we had up here, we had 14 and 1, 14 hydrochloric and 1 potassium dichromate. Okay. If they were gases, which those aren't, but if they were, it would be a 14 to 1 relationship. In volume. Gay-Lussac is relating volume to volume. The normal use of the stoichiometric coefficients in stoichiometry is relating counts to counts, usually moles to moles. Okay. It is never what? Grams to grams. You've always got to get to moles for everything, or volume to volume, the same units for gases. So remember, just because you're using Gay-Lussac's, it doesn't mean those stoichiometric coefficients still don't tell you how many of each one you need in relationship. Moles, dozens, hundreds, whatever your units are. But for gases, they also relate to their volumes. Number 4 from the book, Gay-Lussac's law says that the stoichiometric coefficients in a chemical equation relate the volumes of gases in the equation as well as the number of moles of the substance in the equation. It can be used to relate quantities of gaseous substances in an equation if those quantities are given in volume units. So if you have the balanced stoichiometric coefficients, a balanced reaction equation, and you look and you're told you're given a certain volume of a particular gas within that equation, you then can figure out the volumes of every other gas in that equation. Not every other molecule or element, every other gas. Okay. Number 5. A chemist wants to perform the following reaction. Let's see, CaCO3, calcium carbonate, and 2-hydrochloric acid. This is a gas. I think we might need to know that. This is a solid. Reacts to produce calcium chloride, aqueous carbon dioxide gas. And water liquid. Okay. Okay, so a chemist wants to perform the following reaction. For which substances can she use Gay-Lussac's law to relate them to one another? Which substances can be related using Gay-Lussac? Can we relate? Now, Gay-Lussac, what are we going to compare? Again, we just covered it. We're going to compare volumes to volumes, right? Using Gay-Lussac. It is true that it's 1 mole and 2 moles creates 1 mole, 1 mole, and 1 mole. But for Gay-Lussac, the only things we can even look at using Gay-Lussac are the gases. So this one is not up for consideration. This one is not up for consideration. This one is not up for consideration. Why? They're not gaseous. They're solids and aqueous and liquid. Gay-Lussac doesn't speak to any one of those because it only speaks to those which are gases. And because it speaks to those which are gases, according to this formula, what can I now say using Gay-Lussac kind of a thinking for this formula right here? Okay? Again, Gay-Lussac, I'm relating volumes to volumes, right? In this formula, I can only consider this gas and how it relates to this gas. Tell me a piece of information using Gay-Lussac I can now say given that equation.
2 liters.
Okay. So for every 2 liters of hydrochloric acid gas, right, I will produce 1 liter of carbon dioxide. That's all I can say. Or, other way around, for every liter of carbon dioxide produced, 2 liters of hydrochloric acid gas were used. Okay. But I can't look to any of those other components within the reaction equation using Gay-Lussac because none of them are gases. But at the same time, it is still true that the stoichiometric coefficients in front of every component, reactant and product, in front of every one of them is still true with regard to its relationship for pieces, for moles. Okay? So I can still say 1 mole and 2 moles reacts to produce 1 mole and 1 mole and 1 mole. But using Gay-Lussac, all I can say is for every 2, it produces 1, whatever the volume unit is. So number 5 from the book, the chemist can use Gay-Lussac's law only to relate the volumes of hydrochloric acid and carbon dioxide, since those are the only gases in the equation. Number 6, if a stoichiometry problem gives you a quantity of a substance in grams, what's the first thing you must do to solve the problem? So you're given something in a quantity of something in grams, and you're going to use stoichiometry. What do you have to do? Convert the grams to moles, right? So you're going to have to figure out the molar mass of whatever the substance is and convert your grams to moles. Then when you have moles, then you can use stoichiometry to relate that quantity to any other quantity in the reaction. Okay. Number 6, the answer from the book says, since stoichiometry can be done only in moles or volume in the case of gases using Gay-Lussac, okay? The first thing you must do is convert it to moles. This conversion must be done because the ratio from the balanced equation is in moles, or more accurately, it's in a count unit, of which we typically use moles, right? It could be dozens, it could be scores, it could be hundreds, it could be, whatever. But typically we think of it in terms of moles. Number 7, what's the difference between molecular formulas and empirical formulas? I might use the molecular formula or the empirical formula. What kind of information is in the molecular formula?
Final equation thing.
Okay, so the molecular formula gives me the specific count of every atom that I need to build that molecule. It's going to tell me, okay, from the molecular, I can say, okay, for this molecule, for CO2, it's going to tell me, okay, for every carbon, you're going to need 2 oxygens. It's going to tell me exactly what I need to build the actual molecule. If, rather than that, I come over here to the empirical, could CO2 also be an empirical formula? Okay. The head nod up from the front here says, yes, that could also be an empirical formula. Okay, but if it's the empirical formula, what information do I get from it? It doesn't tell me, okay, for every carbon you have to have 2, and 1 and 2 make 1 molecule. What does this empirical CO2 tell me? It says that when I actually build up the molecule, that my carbons and my oxygens are going to relate to each other in a 1-to-2 ratio. For every carbon, I'm going to need 2 oxygens. But if it's empirical CO2, we have other possible formulas, right? We have multiple possible molecular formulas that it could be. If it's an empirical CO2, it could be C1O2. But what could it also be? And let's just start building it up. It could be a C2O4. It could be a C3O6. It could be a C4O8. See? They're all going to relate to one another in a 1-to-2 ratio. So my empirical tells me when I look into the molecule, for every 1 carbon, I have 2 oxygens. The molecular tells me when I build the whole molecule, I will have only 1 carbon and I will have 2 oxygens, and together they will form a CO2 molecule. All right, so empiricals give you the relationships between the components. The molecular gives you the actual number of components. Yes, sir?
So does the empirical give you the multiple?
Yeah, the empirical allows for there to be multiple formulas. Molecular says, no, this is the one and only. If I look to this and say, okay, my molecular formula is CO2, what are the possible formulas for that molecule? Just CO2. That's it. That's what it is. Mm-hmm. For empirical, my empirical is CO2. What could the molecular be? Multiple options. Okay, because remember, the empirical only relates the amount of each atom in the molecule to each other. Let me read what it says from the book, and we can go from there. It says that the molecular formulas provide the exact number of each type of atom in the molecule, whereas the empirical formulas provide only a simple whole number ratio of atoms in the molecule. A whole number ratio. So the empirical will say, for every 1, I have 2, which means it could be CO2, could be C2O4, could be C3O6. Now, when I say it could be, theoretically it could be, but some of these are impossible because of the way the bonds are formed and everything, right? How are we going to know which one of these is the actual formula? Up till now, we've come up with an empirical formula, and then we've also used a second piece of information to solve the problem. Do you remember what it is? Pardon? The molar mass. Come back and say, okay, or actually more specifically, not just molar mass, but the molecular mass. Say, okay, each one of these molecules has a certain mass to it. I would figure out the mass of the empirical. Then if I was given the molecular mass of the final, this model, right, this molecular formula, if I said, okay, the molecule has a certain mass, what's its actual formula? Well, it'd be a multiple, it'd be one of these. So it may very well just be this one, but you know what? If this formula doesn't have enough mass, it's got to maybe this one. This one, keep adding it up. Keep comparing the mass of the molecule to the empirical. It's going to be a multiple. It's going to be 1 or 2 or 3 or 4 or 5 or 6 or 7. It's going to be, the mass of the molecule is going to be that many multiple times as big as the empirical. And again, actually doing problems with that makes it a lot easier, I believe. Number 8, which of the following are empirical formulas? I'm not going to write them on the board, but let's go through it real quick. If I have a C12H24O10 molecule, is that empirical or is that molecular? It would be molecular. Why? Actually, I'm going to write this on the board just so we can see it. I've got C12H24O10. How do I know that's molecular? I know that's molecular, but how? It can be reduced. Good, Gina. It can be reduced, right? Because if I were interested in taking this formula and writing the empirical for it, I need to simplify it. And given that they're all even numbers, I could very quickly, let's say, divide everything by 2. Well, that would make it a C6H12O5, wouldn't it? Okay. Can I reduce that anymore? No. So this would be an empirical, because these are even, but that's odd. 5 doesn't go into either one of those. This is as simple as I can make it. This would be the empirical of this molecular. K2S2O3. Is that molecular or empirical? Well, and the empirical, remember, could be the molecular, right? But could this one be the empirical? Yes, it could be. Again, because you can't reduce it anymore. 2s and 3s, the only common factor is 1, so it stays the same. And so this would be an empirical. It could also be the molecular, but it is the empirical. And the last one is CaN2O6. Is that molecular or empirical? It's empirical, and every empirical can be molecular because you've got 1 calcium, right? You can't reduce it anymore. 2 and 6 are even, but 1 is odd. The only common factor is 1. This is as simple as it can be. From the book, the formulas given in B and C are empirical formulas because the subscripts have no common factors other than 1. Okay. The formula given in A is not empirical because the subscripts have the common factor of 2. Number 9, and we're almost due. After this we'll do 10 on today's homework, okay? We're almost there. Number 9 from the review questions. A compound has a molecular formula of C14 H21O7. Has a molecular formula of this. What is the empirical formula? The empirical formula of this molecular formula. What I'm going to do is what? How do I reduce this down to an empirical formula? Common factor, right? Common factor here is 7. 7 goes into 7, 21, and 14. So what does the empirical become? That's correct. C2H3O is the empirical formula of the molecular formula C14H21O7. What does this tell me? Okay, when I go through, I'm going to have a molecule, the mass of this molecule, right, in the lab. When I do certain kinds of experiments, I'll receive certain kind of data, and it's going to tell me that I'm going to be in a ratio of 2 to 3 to 1. In this case, we've got carbon, which would be a solid normally at room temperature, but we've got hydrogen and oxygen. Probably whenever we're doing an experiment and collecting like in a decomposition, we're going to have hydrogen in a ratio of 1 to 3. So we've got oxygen being collected off probably over water. We've got hydrogen being collected over water, and then we've got carbon. And we would expect the relationships there because, Gay-Lussac, for example, 3 to 1 would be, I'd have 3 times as much hydrogen being produced as oxygen. Number 10, a compound has a molecular formula of H3PO4. What's its empirical formula? H3PO4, the same thing. It can't be simplified anymore because we have 3 hydrogens, 1 phosphorus, and 4 oxygens. The only common factor is 1. So it can't be simplified any longer. So it is both the molecular and the empirical formula. All right, so that finishes the review questions. Any questions from the review questions? Again, you all did quite well. So if you simply did not copy, but you actually answered from what you understood to be the right answer, you guys are fine in terms of the review questions. Okay. Anything? If not, number 10 from the practice problems from today, right? That's what you asked for us to go over? Number 10 says a dry cleaning compound was decomposed into, so I've got something, was decomposed into 145 grams of carbon and 855 grams of chlorine. In a separate experiment, its molar mass was determined to be 166. 166.0 grams, this substance over here. What is the molecular formula of the compound? Okay. So we have a sense that we're going to be using stoichiometry, right? But we can't use the information in the way it's given. We've been given grams of carbon in grams of chlorine gas. But stoichiometry doesn't use grams, it uses moles. So the first thing we need to do is convert this problem into a mole relationship, not a mass relationship. Now we know that this substance over here, whatever it is going to be made up of what? What are the elements that make up the molecule over here? Carbon and chlorine. We know that we're going to have some amount of carbon and some amount of chlorine. And that's why the X and Y come in. We don't yet know what it's going to look like, but we know it's going to be some amount of carbon and some amount of chlorine. This isn't 4, this is Y, okay? So it's CXClY. Decomposes to produce 145 grams of carbon and 855 grams of chlorine. I wished that I had it in moles over here, don't you? Okay, so let's do it. I do know that 145 grams of carbon, and carbon has a molar mass of 12.0 grams per mole, right? So 145 grams divided by 12.0 grams per mole is going to give me how many moles of carbon I have. And what does that turn out to be? 145 divided by 12, well, 120, I got 25, 2, so it's 12 something, right? 12 and 1/12. What'd you get? 12 point, Brenton, what'd you get? Oh, I thought you were plugging this one in. Well, let me go to the answer key, because that's the cheat. They got it all out here for me. Okay, so 12.1 moles of carbon and 855 grams of chlorine. Chlorine gas is, so 855 grams divided by 35 and a half, so it'd be 71. 71.0 grams per mole. Do you understand how I got these, the 12 and the 71? Each chlorine, remember, is 35.5, so 2 of them is 70. 70.1 grams per mole for chlorine gas, for Cl2. And I have 855 grams of it. So 855 divided by 71, it gives me 12 moles of chlorine gas. So now we're going to look back over and remember that we're looking at relationships. For every 12.1 of carbon, I have 12 moles of chlorine gas. Okay? What's the relationship to each other? Now, it's going to be a little bit of rounding, but in the closest whole number relationship or whole number ratio, it's 1 to 1. Do you see that? The 12.1 and 12.0, the difference there is probably going to be because of rounding and significant figure considerations and things like that. We could go through and divide both of those by 12, but we get 1 and 1 and 1/12, right? So it's a 1 to 1. And so we now know that C sub x, Cl sub y goes to C plus Cl2. How many chlorines? 2 and 1. So carbon would be 1 and 2. Right? I need 1 carbon and 2 chlorines in my original molecule in order to produce 1 carbon and 2 chlorines. Now, this formula right here, what kind of the formulas that we've been working on? What type is this? This is my empirical formula. This is my empirical. So, since my empirical means we discovered it. You know, this is what it gives me. This is what I get. I've learned this empirically. I've learned this by testing. All this is telling me is that for every 1 mole of carbon, I'm getting 1 mole of chlorine gas. Or for every 1 carbon, you know, when it decomposes, I get 1 carbon atom and 2 chlorine atoms, which form 1 molecule. So in my original formula, it's got to be some combination of carbons and chlorine. And my relationship in the original, or in my molecular, is going to be a relationship of 1 to 2. So my empirical is CCl2. What could my molecular be? It could be, first of all, it could be my empirical. It could be CCl2. But it could also be C2Cl4, C3Cl6, C4Cl8, etc. So when they ask me, okay, you figure out that you've got a CCl2 empirical, what is the actual molecule? You're going, I don't know. It could be one of a bazillion of them. All multiples of the original empirical. But that's where the other piece of information comes in, because it tells me that my original molecule, whatever it is, it has a mass of 166, it has a molar mass of 166 grams per mole. Right? 166 grams per mole. And it's made up of carbons and chlorines in a proportion of 1 to 2. So let me look at my empirical, and let's compute the molar mass of my empirical molecule. I've got a carbon, which is 12.0, and I've got 2 chlorines, which is 71, which is 83.0 grams per mole. So my empirical is 83 grams per mole. My actual is 166 grams per mole. So what's my factor? My actual is 166. My empirical is 83. My factor is 2. I take my empirical and I multiply every subscript by the factor of 2. And when I do that then, CCl2 as the empirical means that my molecular is C2Cl4. Okay? Because my actual molecule is twice as massive as my empirical molecule. There's my empirical. There's my molecular. So my empirical tells me when I actually eventually make my actual molecule, I'm going to need carbons and chlorines in a proportion of 1 to 2. But now that I know the molecular, I say when I actually go to construct that molecule, it's going to be 2 carbons and 4 chlorines. If I have 2 carbons and 3 chlorines, I can't make it. Now, one of the things that might seem a little bit existential, like a little bit out there, is this whole idea here that you're not always going to get the nice 12.1 to 12.0, okay? And this right here, you look at it and go, hey, it's a 1-to-1. Yesterday we did a problem, and it was fractional. Remember, it was like 0.08 something and 1.66, you know. You get these different things, different numbers, but you're still looking at how they relate to one another. If I said, and please bear with me, listen up just for a moment, I won't keep you long, but let's say their coefficients on one side were 1/2 and 3/4, you know? How do they relate to one another? Well, you could say, well, how many times does a half go into a half? It goes in there one time. How many times does a half go into 3/4? 1.5 times, right? It goes in there 1.5 times. Oh, that's not good enough. I need whole number ratios. What might I then do? I multiply it by 2, and I get 2 and 3. Okay, there's my relationship, 2 to 3. So all you're doing when you have fractionals is dividing by one of them to see if you can get how proportional they are to one another. And that'll give you your coefficients for your stoichiometric balanced equation.